Welcome to Cybersecurity Under Pressure. Real attacks, real lessons. Every breach starts with something small. A trusted login, a missed alert, a system no one thought could matter. Here, we follow the incident. How it began, how it moved, what broke under pressure, and what security engineering and business teams should learn before the next one. Because the next attack will not wait for a perfect plan. Now, let's follow the evidence.
Welcome to Cybersecurity Under Pressure, Real Attacks, Real Lessons. Today is Friday, June 26th, 2026. And I don't know about you, but I am very much feeling that Friday exhaustion right now.
Oh, yeah. It has been one of those weeks. I can hear it in your voice.
Man, I spent literally Monday through Thursday trying to implement a relatively standard, modern encryption patch on a legacy industrial controller system, and it just gave up the ghost. It completely died.
I mean, yes, you triggered a hard fault on a legacy chip, didn't you?
Yes, it didn't even try to process it. Like, the handshake latency alone from the modern cryptography, it timed out the hardware watchdog, and the entire system just threw its hands up and power cycled. It is so infuriating. You're trying to force contemporary computational math onto silicon that was designed back when, flipping a basic logic gate was considered heavy lifting.
Which, that perfectly encapsulates the structural nightmare of modern engineering right there. You're basically trying to bolt a biometric retina scanner onto a canvas tent. The structural integrity of the foundation just can't support the security apparatus you're legally required to install.
Continuidad de tema. De hecho, The Wire Transfer acaba de publicar algo relacionado, el mismo vector, diferente industria. They were looking at OT security, remote access, and honestly, the pain points they highlighted are identical to what I just dealt with.
Oh, absolutely. The underlying physics of the problem don't change just because the industry does.
Right. But that frustration, that physical friction between ancient hardware constraints and modern aggressive cyber threats, that is exactly what we are unpacking in this deep dive.
And there is no sector, absolutely nowhere, feeling that friction more violently right now than the automotive supply chain.
Exactly. So for this deep dive, we're taking a massive stack of source material. We've got the Vicon 2026 Automotive Cybersecurity Report, some really fascinating interview studies from the DIVA portal on actual compliance implementation, and of course the unvarnished legislative texts of UNES R155 and the EU Cyber Resilience Act.
Light reading for a Friday.
Oh yeah, total beach reads. But our mission today is to synthesize all of this and figure out how the automotive supply chain is supposed to survive this regulatory avalanche, right? Without grinding innovation to a halt, or honestly just faking their compliance. Because right now, the modern connected vehicle is essentially a massive data center.
A data center hurtling down a highway at 80 miles an hour, which is a terrifying thought. We're talking about platforms housing upwards of 100 million lines of code.
100 million. I always try to visualize that. It's more code than a commercial airliner. It's more than a modern fighter jet.
Way more.
And the chaos multiplier here is that this code base isn't compiled by, a single cohesive team sitting in a room in Munich or Detroit.
No, not even close. You're looking at a deeply fragmented ecosystem of over 150 distinct suppliers for a single vehicle platform.
150.
Yeah. You've got your tier 1s providing these massive domain controllers, your tier 2s providing the RTOS, the real-time operating systems, and then the tier 3s supplying these microscopic black box binaries that everyone just, assumes are safe. It's an amalgamation of proprietary code, commercial off-the-shelf software, and deeply embedded open source libraries.
Which makes it a spectacularly target-rich environment. And because we've insisted on connecting every single one of these mobile data centers to the cloud, the regulatory bodies have finally panicked. They are dropping this absolute alphabet soup of frameworks on engineering directors.
Alphabet soup is putting it mildly. It's a regulatory tsunami.
Right. And I want to start by tearing apart two of the biggest frameworks that are currently just suffocating security teams. TISOX and ISSA 2434, because I hear people conflating these constantly. They throw them into the same generic compliance bucket, but mechanically they are solving entirely different vectors.
Confusing them is a phenomenally expensive mistake, too. The easiest way to conceptualize the difference is that TISAX is an enterprise risk framework, whereas ISO 21434 is an engineering lifecycle framework. So TISAX, Trusted Information Security Assessment Exchange, is fundamentally about walling off the corporate organization.
Right, it's basically ISO 27 Sour 1 on steroids, custom tailored for the European automotive supply chain.
Pretty much, yeah. It's managed by the ENX Association. Think about the intellectual property at stake here. If an OEM shares the unreleased CAD drawings for a 2028 EV platform, or raw telemetry data from customer fleets with a Tier 1 supplier, the OEM needs an ironclad guarantee that the Tier 1's corporate network isn't going to be completely compromised by some ransomware syndicate.
So they need AL3 assessment level 3 for that high protection data.
Exactly. TISAX mandates secure corporate networks, stringent identity access management, even physical security, like making sure someone can't just walk into the R&D facility with a USB drive and walk out with the braking algorithms.
Okay, so TISAX is guarding the perimeter of the factory and the IT servers, putting a giant padlock on the corporate doors. But ISO 21434 is guarding the actual metal and code rolling off the assembly line, making sure the product doesn't explode in the customer's face.
Precise. Well, it goes far deeper than just guarding it. ISO 21434 dictates that cybersecurity must be fundamentally woven into the DNA of the vehicle, from the concept phase all the way through decommissioning.
The whole V model of engineering.
Right. It introduces the Terra process, threat analysis, and risk assessment. It mandates secure coding guidelines, vulnerability management, continuous monitoring. If TISAX prevents a threat actor from stealing the blueprints for a braking controller off an IT server, ISO 21434 prevents a threat actor from injecting malicious CAN bus frames to disable those physical brakes while the vehicle is actually in motion.
Okay, I understand the theoretical boundary there. IT protects the blueprints, engineering protects the brakes. But I'm going to push back on how this is actually implemented in the real world. Shouldn't these be completely siloed? I mean, the skill set required to configure a firewall for a corporate HR server is wildly different from the skill set required to analyze the attack surface of a deterministic real-time operating system running on a microcontroller.
You'd think so. And traditionally, yes, that's exactly how companies have treated them. IT sits in one building sweating over TISAX, and the embedded engineers sit in a basement somewhere sweating over 214-324. But siloing them is exactly what's causing the current operational breakdown we're seeing. We are seeing massive audit fatigue because of duplicated efforts.
Duplicated how? Like paying for the same thing twice.
Basically, look at the overlap in foundational governance. Both frameworks require a baseline of identity and access management. Both require incident response capabilities. If you silo them, your supplier ends up paying two different audit firms to review essentially the same core organizational competencies, just framed slightly differently.
That sounds like a great deal for the auditors.
Oh, it's incredibly lucrative for the consultants. But more importantly, from a security standpoint, the technical barrier between IT and OT, between the enterprise network and the vehicle, is disintegrating. The SolarWinds attack taught us that.
Ah, supply chain poisoning.
Exactly. If your corporate IT network is weak, meaning you fail TISAX, an attacker can pivot laterally from an HR server, compromise an engineer's workstation, and inject a backdoor into the firmware build pipeline. The firmware gets cryptographically signed because the build server trusts the engineer's workstation, and boom, you've just pushed a compromised OTA update to 1 million vehicles. That is a 21434 engineering failure that was directly caused by a TISAX IT vulnerability. You cannot silo these domains anymore because the attackers certainly aren't siloing their attack paths.
That makes a terrifying amount of sense. The corporate network is really just the staging ground for the vehicular payload. And this complete blurring of lines brings us to the massive regulatory hammer that just dropped. Because prior to 2024, ISO 21434 was just, a really good idea. It was a standard. But UNES R155 turned it into the law.
It did, and the industry is still reeling from that July 2024 enforcement deadline. R155 is a mandatory type approval requirement across 64 countries. The EU, Japan, South Korea, the UK, if you want to sell a vehicle in these markets, compliance is a hard, non-negotiable precondition. You literally cannot sell the car.
Right.
And R155 operates on two distinct pillars.
The CSMS and the type approval, right.
Right. Pillar 1 is the Cybersecurity Management System, or CSMS. This is the overarching organizational certification. It proves the manufacturer has the actual governance, risk management frameworks, and incident response structures in place across their entire operation. And that certificate is valid for a maximum of 3 years.
And you can't even touch Pillar 2 without passing Pillar 1.
You absolutely can't. Pillar 2 is the vehicle type approval. This is the highly specific product-level assessment where you prove that for this exact vehicle architecture, say, the 2027 model year of a specific EV platform, you have meticulously identified the risks, implemented the mitigations, and validated the security controls.
And this is where the dynamic between the OEMs and the lower-tier suppliers gets incredibly toxic.
Oh, it's brutal.
The OEMs, the big brands, whose badges are actually on the steering wheel, they hold the ultimate legal liability for that type of approval. If the car gets hacked, it's their brand on the front page of the Wall Street Journal. But they don't write all 100 million lines of code, so their reaction is to just contractually outsource their compliance anxiety down the chain.
Outsourcing compliance anxiety is a brilliant way to phrase it, because that's exactly what it is. The OEMs need a mountain of evidence to hand to the type approval authorities. So they turn to their Tier 1s and demand full Terra documentation and a compliant CSMS. The Tier 1s panic, spin around, and demand the exact same thing from the Tier 2s and Tier 3s.
I was reading through the Diva portal interviews from the source material, and there was this one anecdote that genuinely raised my blood pressure. A Tier 2 supplier, a relatively small company making basic electronic subcomponents, was forced by an OEM to prove compliance. They ended up spending 80,000 euros on external consultants just to generate the necessary documentation.
Just for the paperwork.
It's for the paperwork. And the interviewee explicitly noted that their actual technical cybersecurity posture didn't improve by a single cent. They bought an 80,000 euro PDF.
The 80,000 euro PDF.
Yeah.
It's the darkest reality of these regulatory frameworks. When you apply massive pressure to a supply chain without providing the necessary tooling or standardized methodologies, you don't get better engineering. You get a cottage industry of consultants generating paper compliance.
But break down the mechanics of why that happens. If I'm a Tier 2, right, and I'm legally forced to conduct a threat analysis and risk assessment under ISO 21434, shouldn't that inherently force me to look at my code and fix the bugs? How do you spend 80 grand and not fix anything?
Because of how risk assessment frameworks are mathematically manipulated. So, Annex 5 of the R155 regulation lists 69 specific attack vectors. Everything from spoofing messages on the internal communication channels to manipulating over-the-air update packages.
Okay, tracking so far, 69 vectors.
The Tier 2 supplier hires a consultant. The consultant builds a massive Excel spreadsheet mapping the supplier's tiny component against those 69 vectors. Now, to determine if a vulnerability requires actual engineering mitigation, you have to calculate its risk value, which is usually a combination of attack feasibility, how hard is it to pull off an impact.
Advanced risk matrix.
Exactly.
Yes.
But if the Tier 2 lacks the budget or the hardware capability to actually implement strong encryption on their ancient microcontroller, the consultant will simply argue in the documentation that the attack feasibility is incredibly low because, quote-unquote, the component is deeply embedded and theoretically inaccessible from the outside world.
So they just mathematically massage the risk score down to an acceptable level. They just say, well, it's fine that this component uses plain text communication because a hacker would need physical access to the wiring harness under the passenger seat.
Exactly. They document the accepted risk, generate a 400-page terror report, hand it to the Tier 1, who hands it to the OEM, who hands it to the regulator. Everyone's legal liability is covered. The 80,000 euros was spent entirely on legal friction, while the underlying hardware remains fundamentally insecure.
Which completely ignores how modern threat actors actually operate. I mean, they don't need physical access to the wiring harness, they pivot remotely, and the data we have from the Vicone 2026 report shows that this paper compliance illusion is shattering in real time.
The Vicone data is genuinely sobering. It proves that the era of isolated, domain-specific attacks is over. Hackers aren't just trying to, clone a key fob anymore to steal a car from a driveway. They are executing complex, multi-stage kill chains that span enterprise IT, off-board cloud infrastructure, and the in-vehicle network simultaneously.
Let's unpack the mechanics of that, because the Vicone report highlighted a statistic that I just couldn't stop thinking about. 33% of cyber risk now directly impacts the driver experience. The attackers are moving out of the deep, invisible back-end systems and explicitly targeting the user-facing integration layers. How are they physically pivoting from an external connection to something that affects the driver in the cabin?
It comes down to the architecture of the modern software-defined vehicle. To save money and weight, OEMs are consolidating dozens of distinct electronic control units into single, massive domain controllers. So you might have the Android Automotive OS, which handles your Spotify, your navigation, your Bluetooth, running on the exact same physical silicon as the real-time operating system that monitors the vehicle's telemetry.
But they are isolated, right, by a hypervisor, like a virtual machine setup.
Theoretically, yes. A hypervisor is supposed to create an impenetrable virtual wall between the infotainment OS and the critical deterministic systems. But hypervisors are just software. They have vulnerabilities. A sophisticated attacker will compromise a third-party companion app on your phone, use that to exploit a Bluetooth stack vulnerability to gain root access to the infotainment system, and then execute a hypervisor escape.
Meaning they punch a hole through the virtual wall.
They find a shared memory buffer or a misconfigured virtual switch, and suddenly they're dropping malicious payloads directly onto the CAN bus, which controls the physical steering and braking. That's why the driver experience is being impacted. The infotainment system is the most accessible attack surface, and the hypervisor boundaries are proving porous.
And the sheer volume of these vulnerabilities is staggering. The report cited 174 zero-day vulnerabilities uncovered at Ping2-owned Automotive just since 2024.
174.
And a zero-day means there is no patch. The manufacturer doesn't even know it exists until the researchers exploit it live on stage.
Which completely invalidates those 80,000 euro static TARA spreadsheets we were just talking about. A static risk assessment assumes a static threat landscape. But when you have almost 200 zero days dropping in a 2-year window, your threat landscape is highly dynamic. If your security posture is based on the assumption that a specific hypervisor wall is impenetrable and a 0-day renders that wall useless, your entire risk calculus collapses overnight.
And this ties directly back to my hardware failure earlier this week. It's the problem of structural risk and legacy silicon. Car life cycles are incredibly long. If you buy a vehicle today, it's going to be on the road for 10, maybe 15 years.
Easily.
If an OEM discovers a critical cryptographic flaw in a powertrain controller 3 years from now, how do they fix it if the silicon physically cannot process a heavier encryption algorithm?
They often can't. That was a major theme in those Diva Portal interviews. Engineers explicitly admitted they face brutal performance versus security trade-offs every single day. Older components simply weren't designed with cybersecurity overhead in mind. If you try to force an RSA 2048 encryption key exchange on a chip designed to manage windshield wipers, the processor load spikes to 100%, the timing requirements fail, and the wipers stop working.
This system crashes, just like my legacy controller. It timed out the watchdog. So what do? They can't just sell a car without windshield wipers.
They degrade the security, they use shorter, weaker encryption keys, or they abandon encryption altogether and just rely on a basic checksum for message integrity. They accept the structural risk because the alternative is a non-functional vehicle. And because automotive architectures carry forward across multiple vehicle generations to save R&D costs, that compromised legacy component might end up in the 2028 model year, simply because re-engineering it from scratch is too expensive.
Wow. So you have a supply chain drowning in R155 compliance, faking TARAs for legacy hardware that can't actually handle modern cryptography, while attackers are chaining 0 days through infotainment hypervisors.
A mess.
It really is. And just when you think the regulatory environment couldn't get any more complex, the European Union decides to flip the table entirely. Let's talk about the CRA, the Cyber Resilience Act, because I know engineering directors are losing sleep over this one.
Oh, the CRA is the ultimate wildcard. If R155 was a targeted strike on the automotive sector, the CRA is a carpet bombing of the entire digital ecosystem. It is a horizontal piece of legislation that applies to fundamentally any product with digital elements placed on the EU market.
But here is the massive point of confusion I see everywhere, and I want to clear this up for you, the listener, right now. Aren't cars exempt? I keep seeing executives breathing a sigh of relief on LinkedIn because they think type-approved vehicles get a free pass under the general safety regulation.
That is a highly dangerous misinterpretation of the text. Yes, the fully assembled type-approved vehicle itself is technically exempt from the CRA because it's already governed by R155. But the CRA applies to almost everything surrounding it. We are talking about aftermarket components, retrofit modules, standalone ECUs sold directly to consumers, connected mobile companion apps, and critically, EV charging infrastructure.
Hold on, let me trace that logic. So if I am a tier 1 supplier, right, and I manufacture a telematics gateway, if I sell that exact gateway directly to BMW to install on the assembly line in Munich, that gateway is covered under BMW's R155 umbrella.
Correct.
But if I take that exact same telematics gateway, put it in a cardboard box, and sell it on the aftermarket as a replacement part, so that's I am fully bound by the CRA for the exact same hardware.
That is exactly how it works. You have dual compliance scenarios for the exact same piece of silicon. And the CRA has real teeth. It requires a formal CE marking, elevating cybersecurity to a fundamental safety requirement for market access. If you fail to comply, market surveillance authorities can force a total product recall across the entire EU, and they can levy fines up to 15 million euros or 2.5% of your global turnover, whichever is higher.
That is existential threat territory. You could go bankrupt.
Yeah.
And full compliance is mandatory by December 2027. So what is the CRA actually demanding that makes it so much more terrifying than R155?
The mandate that is keeping the entire industry awake at night is the mandatory machine-readable software bill of materials, the SBOM.
Okay, let's dissect the SBOM. Because the concept sounds deceptively simple to an outsider. It's an ingredient list, right? The government is finally demanding that software vendors print the nutritional label on the back of the box. This product contains 10% proprietary code, 40% open source Linux kernel, and 50% mysterious third-party libraries. Why is an ingredient list causing such a panic?
Because, to continue your analogy, you were trying to reverse engineer a fully baked wedding cake back into its original flour, sugar, and eggs. But the flour was milled in a factory that went bankrupt 5 years ago, and the eggs came from an open source farm that no one monitors.
That is brilliant and horrifying.
The CRA explicitly requires manufacturers to identify and document every single software component, including transient dependencies, meaning the libraries that your libraries rely on, in a standardized machine-readable format like SPDX or CycloneDX. The philosophy is that you cannot secure what you cannot see.
Which makes total sense from a security standpoint. I mean, if another Log4j vulnerability drops on a Friday afternoon, a company needs to query a database and know instantly if their fleet is exposed. They can't spend 3 weeks emailing Tier 3 suppliers asking, hey, did you use this logging library in 2021? But the market research shows a massive automotive SBOM gap, doesn't it?
The gap is structural. By some estimates, fewer than 30% of Tier 2 and Tier 3 suppliers have implemented automated SBM generation workflows. When an OEM asks a small supplier for an SBOM today, they don't get a machine-readable SPDX file. They get a manually typed PDF that was updated 6 months ago by an intern.
And it gets even worse when you deal with legacy binaries, right? What happens when an OEM has, say, an AUTOSAR component that was compiled by a supplier in 2020, the supplier went out of business during the pandemic, and all the OEM has is the compiled, stripped binary file. There is no source code to look at.
That scenario requires what the industry deeply dreads. They call it component archaeology.
Component archaeology. That sounds like a tremendously expensive use of compute power. How do you extract an ingredient list from a stripped binary?
You have to utilize advanced software composition analysis, or SCA, specifically designed for binary analysis, and it is highly complex. Since the human-readable source code is gone, the SCA tool has to disassemble the machine code, generate control flow graphs, and look for specific bytecode signatures or structural patterns. It then compares those patterns against massive databases of known open-source libraries.
So it's basically pattern matching the compiled architecture to guess what the original library was.
Essentially, yes.
Sure.
And it's incredibly difficult on embedded automotive architectures like ARM Cortex-M because the compilers aggressively optimize the code to save space on those tiny chips. They strip out all the metadata, they inline the functions, and they completely mutate the structure. So the SCA tool might flag a cluster of code and say, well, we're 85% confident this is a vulnerable version of OpenSSL.
85% confident, which means a human engineer still has to go in, look at the disassembly, and manually verify it. And you have to do this for 100 million lines of code.
Exactly. And the CRA makes this transparency non-negotiable. If a market surveillance authority sends you a recent request, you must produce that SBOM. The burden of proof has entirely shifted from the regulator finding a flaw to you proving you know every line of code in your product.
So let's pull all of these threads together for you listening right now, because we've mapped out a genuinely brutal landscape. We have Tyzex and 21434 operating in these massive inefficient silos. We have OEMs crushing Tier 2 suppliers with R155 paperwork that doesn't actually secure the legacy hardware. We have multi-stage attacks pivoting through infotainment hypervisors. And now the CRA is demanding machine-readable component archaeology by 2027. How does a supplier survive this without their margins completely collapsing under the weight of compliance?
Survival requires a fundamental shift in strategy. You have to harmonize the chaos through automation. You have to stop treating Tyzex, R155, and the CRA as separate, isolated regulatory hurdles.
Okay, but how does that actually manifest in a company's workflow? It's easy to say harmonize, but what does the engineering team actually do?
It starts at the governance level. If you properly implement the CSMS required by ISO 21434, you shouldn't just be doing it for the vehicle. You use that exact same governance structure to capture the risk assessments needed for R155 and to establish the secure by design evidence mandated by the CRA. You map the controls. The access management policies you implement for TISAX to secure your HR servers, those should be extended to secure your firmware build pipelines. You build the evidence once, and you route it to the specific regulatory audits.
Merging the silos, that solves the organizational overlap. But what about the technical burden? How does a Tier 2 supplier solve the SBM gap without hiring an army of reverse engineers?
You have to shift left and automate the generation. The days of treating an SBOM as an audit artifact you generate at the end of a project are over. It has to become an engineering artifact. You integrate automated software composition analysis directly into your CI/CD pipelines. Every single time a developer commits a new line of code or updates a third-party library, the pipeline automatically compiles the code, runs the analysis, and dynamically updates the Cyclone DX file.
So the ingredient list is always perfectly synchronized with the current build.
Exactly. And then you plug that dynamic SBOM into an automated threat intelligence feed. Instead of a security analyst manually reading CVE reports on Twitter, the system continuously cross-references new vulnerability disclosures against your live SBOM. If a new zero-day drops that affects a specific Bluetooth library, the system instantly flags exactly which vehicle platforms and which specific firmware versions are utilizing that library.
That moves you away from static paper compliance, the 80,000 euro PDF, and into continuous monitoring, which realistically is the only way to manage a 15-year vehicle life cycle. But continuous monitoring is useless if you can't actually deploy the fix. Which brings us to the critical dependency, over-the-air updates. OTA.
OTA is the absolute lifeline of modern vehicle security. R155 and the CRA both implicitly demand it because they require vulnerability remediation throughout the product lifecycle. If you detect a flaw, you cannot ask 2 million customers to drive to a dealership to flash a module via the OBD2 port. The logistics are impossible. You need secure OTA.
But OTA is an incredible attack vector in itself. I mean, if I'm an attacker, I don't want to hack one car. I want to hack the update server and push a malicious firmware payload to the entire global fleet simultaneously.
Which is why the OTA infrastructure must be fortified with multiple layers of cryptographic trust. You need hardware trust anchors in the vehicle, verifying the cryptographic signature of the update package before it even unpacks it. You need AB partition updates, so if the new firmware fails or is corrupted, the vehicle seamlessly rolls back to the known good state without breaking the car.
And yet, as sophisticated as that sounds, I can't shake this feeling that we are entirely missing the broader physical risk. We spend all this time worrying about data privacy and individual vehicle safety, but there's a macro-level threat here that I want you to think about. We touched on EV charging infrastructure being pulled into the CRA earlier.
Yes, the charging ecosystem is highly vulnerable. It's a massive blind spot.
Think about the ISO 15118 protocol, the plug-and-charge communication standard between the car and the grid. If an attacker leverages one of these hypervisors 0 days we talked about to build a botnet of, let's say, 250,000 compromised electric vehicles, they don't mess with the brakes, they don't steal user data, they just wait until a peak load event, say a massive heat wave in California, and they trigger all 250,000 vehicles to negotiate maximum rapid charging draw from the grid simultaneously.
Oh, wow. A coordinated high wattage demand spike.
Exactly. The local transformers physically melt. You destabilize the regional power grid not by hacking the utility company, but by weaponizing the automotive supply chain. The vehicle isn't just a data center anymore, it's a grid-attached high-voltage appliance. If our compliance regimes are just generating 80,000 euro PDFs instead of actually hardening the code, we are leaving critical national infrastructure entirely exposed.
That is the ultimate consequence of the overlap era. The attack surface isn't just the car anymore, it's the entire ecosystem. And an illusion of security built on static paperwork and siloed audits is far more dangerous than knowing you are vulnerable.
It really is a staggering amount of responsibility sitting on the shoulders of embedded engineers right now. They aren't just protecting blueprints or stopping cars from crashing, they are literally defending the stability of the grid.
It's monumental.
Oh.
But by dismantling those silos, embracing automated SBOMs, and moving toward continuous hardware-backed resilience, it is a fight the industry can win. We just have to evolve past the paperwork.
Well, on that note, I think we both need another coffee before dealing with any more legacy silicon today. That's all for this episode of Cybersecurity Under Pressure. Real attacks, real lessons, check your PLCs, check your logs. And maybe question whether that air gap is really an air gap when your car is downloading an OTA update on the highway. Stay secure out there.
have been listening to Cybersecurity Under Pressure. Real attacks, real lessons. Real incidents leave real lessons. Stay prepared, stay critical, and keep following the evidence.